This lecture is going to cover how we include damping in modal analysis. So for a damped system, this is the governing equation. We have mass, stiffness, as we've talked about already, but we also have a damping matrix and velocities involved. And we talked last time about the fact that for the undamped system, we can find the free response by assuming a solution of the form some shape scaled by an arbitrary constant e to the I omega t. And that allowed us to solve this. That leads us to this eigenvalue problem, which we can then solve. And this gives us the natural frequencies and mode shapes of the system. If the system was undamped, we could then do a coordinate transformation where we replace these variables q with phi times eta. And as we do that, we end up with an uncoupled system of equations. And so this is, remember, one of the key derivations in this class, and something that you should know how to do very readily by the time we're done. And there's just a couple of steps. We plug this in up above in these three places, and then we pre-multiply by phi transpose every term. And in the case of the undamped system, this one becomes an identity times the eta double dot. This one becomes a diagonal matrix of natural frequencies squared times the eta. And then we could also have a forcing on the other side. But what do we do about the damping? What happens here? Well, the equations of motion will only be uncoupled if that matrix is diagonal, or if after multiplying phi transpose c phi, we get a diagonal matrix. So if that's the case, if we do get a diagonal matrix, then looking at the equations here, what we want to do is on the diagonal have every term be the corresponding damping ratio and natural frequency. And then the form would exactly match the form that we're used to for a single degree of freedom system. So the eta dot term has a 2 zeta omega n. And then everything that we've done for single degree of freedom systems, we could then do there. So this is the easy case. If this happens, everything will go great. So under what conditions will the C matrix be diagonalized? And there are a few different cases we'll talk about. And the book talks about this and mentions the light damping approximation. So what are the ways that this is done in practice? I would say that this first one is the most common, one of the most common at least. And usually when we're modeling a structure, we just don't even know what the C matrix is at all, right? We have no idea what the damping matrix is. There aren't a bunch of dash pots connected to our structure. It's a steel structure like an airplane or a rocket. So what we would do is we would just go through this whole analysis, and then rather than insert a C matrix here, we just start right here at this point. And at this point we say, let's insert that term, and let's assign the damping ratio based on past experience. So for example, for aircraft, often 1 or 2% damping, so zeta 0.01 is a typical value. When doing flutter predictions for aircraft, so this is vibration of wings of aircraft we talked about earlier in the semester, some of the standards dictate that you use 3% damping for those calculations, or a minimum. If you can show your structure has more damping than that, you can use a larger value. Another interesting tidbit every material has some amount of damping, and sometimes you can look that up in tables. For example, a steel bar, if we put it in vacuum so that there's no extra damping from the air, air carrying away energy or anything else, they've measured that the damping tends to be on the order of 1/10,000th of, or 1/100th of a percent, or 1/10,000th for the damping ratio. So you can go look up numbers like that, and you can use those. For aluminum, it'll be a little higher. For plastics and rubbers, it would be a lot higher. And so you can look those things up. By the way, if you're interested in understanding what causes the intrinsic damping in materials, there's a class, EMA 630, viscoelastic materials, that talks about that and how that's modeled, and the fundamental physical kind of material processes that cause that to come about. For a material like steel, it's actually slipping, sliding, friction at the grain boundaries that causes the damping. Though people have done interesting experiments on single crystals at the micro scale, and then you have other effects, thermoelastic effects, and all kinds of crazy things that can cause damping. But anyway, all structures have damping, and this is the approach I use the most, is just to ignore it in this stage, and then when we get down to having the uncoupled equations, we will put it in right there. All right, another approach is to calculate a damping matrix. If you have a high fidelity model, maybe a fluid structure problem, or maybe you're doing a car where you have dash pots and you know what their damping properties are, the suspension of a car. Or maybe you have a viscoelastic material. You've taken EMA 630, you figured out what the damping in your material is, and you have a few different materials coming together and you build a damping matrix. So in that case, we can actually calculate this product, phi transpose C phi, and the result of that calculation we call C hat. That's the matrix that we would like to be diagonal. And this approach is called the light damping approximation. And it typically works well, and basically what we do is we just ignore all the off-diagonal terms, and we keep only the diagonal there. And then each diagonal term, which incidentally is a product, C11 is phi 1 transpose C phi 1. So this is a property of mode 1 only. But anyway, we assign that value to be 2 zeta omega 1. And so we can solve for zeta 1, it's just whatever we got for C11 over 2 omega 1. So we assign the damping ratios that way. And this approach typically works really well if the damping is less than 10%, which is typical for engineering structures. But you can come up with some crazy counterexamples where you have a really large off-diagonal term where interesting things happen that are important, that are neglected. So so that's one approach that we can do. The light damping approximation. All right, so and then last but not least, if this triple product phi transpose C phi, that's a transpose there, happens to be diagonal, then the system is what we call proportionally damped, or it does have classical normal modes. And in that case, we just match the terms, and as we talked about up above, and we can proceed. Now, I should mention that it's not such an impossibility to have a damping matrix that isn't diagonalizable. And chapter 10 in the book actually talks about how we can deal with that. If we put the system into state space, as you're used to doing to be able to integrate the equations in OD 4.5, we can actually solve an eigenvalue problem in state space, and everything works out just fine. We can still come up with analytical solutions. It's not a problem. And so these state space modes aren't typically used a lot in industry, but that is a possibility. Most of the time, though, in industry, we don't even have a damping matrix. We're using this first approach. And so it's simpler just to use the classical modes. One of the challenges with the state space approach is that the mode vectors, those mode vectors phi, become complex variables. And everything, just gets a little bit more complicated. So a professor at Caltech in the 1960s approximately studied this problem, and it's interesting. He was studying damping long before we had computers that could calculate mass and stiffness matrices for real structures. But he was a theoretician and kind of forward-looking, and he came up with some theorems. He was able to prove that if M inverse C and C M inverse, if those two were equal, and the same for the stiffness matrix, that the system has classical real modes, or that the damping matrix will be diagonalized. So he came up with something called a Kagi series, which says that if the C matrix can be written as the product of M and then this summation of these matrix products, that the system has classical real modes. So these two aren't used all that much, but they are theorems that can be used to come up with a damping matrix. The one that he's also credited with, I think, that you see a lot is this special case of these conditions, which is that the damping matrix is some constant alpha times the mass matrix plus some constant beta times the stiffness matrix. And if that's the case, if we multiply phi transpose C phi, notice that this first term is going to give us alpha times phi transpose M phi, right? Or that's just alpha times an identity matrix, right? And that second term is going to give us beta times phi transpose K phi. And what is that? Phi transpose K phi is a diagonal matrix with the natural frequencies squared along the diagonal. So first natural frequency squared, second natural frequency squared, and then everywhere else we'll have zeros. So again, if you understand this fundamental derivation in about 2 seconds, you can derive that the damping, the diagonal of this matrix, will be alpha plus beta omega n squared. And so we have two numbers that we can pick to get the damping ratios that we want for every mode. Typically this isn't something that's used because we know fundamentally what the alpha and beta for a system are. We're usually just using this as a way to give the system the damping that we want. So we set that equal to 2 zeta omega n, or actually this should be 2 zeta j omega j for a general system. And the damping then would be zeta, or the alpha term over 2 omega n plus the beta term times omega n over 2. So the challenge with this approach is if we have a multimode system, the damping due to the beta term is going to increase with frequency. So if we were looking at the magnitude of the transfer function, we would see the peaks getting lower and lower and lower, or more heavily damped as frequency goes up. And in contrast, the alpha term has damping that goes up with frequency, or that goes up, that's high at low frequency, really high at low frequency, and then it goes down, so the amplitude goes up with frequency. So if you add those two together over a small enough frequency range, you can get something, maybe where the damping will be constant with frequency. Like that. And that's typically what's observed. That's what's observed more or less in experiments for real structures, real materials. So that's the proportional damping, the mass and stiffness proportional damping approach. And this is common. You can use this in ANSYS, in Nastran, in other finite element packages. And so that's a very common approach for assigning the damping to a structure. For example, in Nastran or ANSYS, if you want to do a transient analysis with damping, but you don't do modal analysis, for example, if you have a nonlinear system or some system where you can't do modal analysis first, this is the approach that's typically used to give the system damping. And you eventually will just have to accept the fact that if you go to high enough frequency, the modes are all going to become very heavily damped, but you just hope that this frequency, that these are, that this happens above the frequency that you're interested in. Okay, so with our 2 degree of freedom system example that we've done earlier, suppose we wanted both the damping ratios to be 0.01. Again, what we would do is we would just take the undamped equation we had, which had these two terms, and we would just add in this damping term. And then now we have a damped single degree of freedom system that we're going to have to solve. And so where before we used the real form, now we can we might have to use the damped form, which was real of a e to the lambda t, where lambda is negative zeta omega n plus I omega d. So we can use one of those forms for the system, for the solution. Okay, so this is how we handle multi-degree of freedom systems with damping. One interesting application of this is earthquakes. I don't know if you watch the news, but just a couple weeks ago there was a sizable earthquake near Salt Lake City, Utah. I have some family living there, and that morning of these earthquakes, my phone exploded with text messages as everyone was talking about it. It wasn't powerful enough to do tons of damage. The biggest one was a 5.7. Though it did do, some considerable damage in downtown Salt Lake. But it was kind of unique in that it was a pretty long earthquake. The ground shook for several seconds. I think it was 10 or more seconds. So, it's one thing to feel an earthquake. It's even more frightening when it goes on and on for a long time. I actually grew up in California, so earthquakes were something we thought about a lot. In 1989, I remember this earthquake. It was epicentered here in the Bay Area, and I was living out in Stockton in California. But this was almost a 7.0 earthquake and did tremendous damage throughout the Bay Area, at least 63 people killed, and many, many homes destroyed. So pretty serious earthquake. And, I was a 2 or more hour car drive, more than 100 miles away. And I remember just getting home from school, looking in the backyard and seeing huge tidal waves splashing in our swimming pool from the shaking of the ground. But on a more serious note, earthquakes can be very, very deadly, very serious. In the Bay Area quake, we were fortunate that most of the houses are built to withstand them or built to high construction standards, except for certain parts of town where they had a lot of problems with houses sliding off their foundations. In Haiti, a similar magnitude earthquake destroyed thousands, hundreds of thousands of residences and killed at least 200,000 people. So a terrible, terrible tragedy. And a lot of those deaths could have been avoided if buildings had been built to higher standards. The concrete cinder block construction that they use was not up for that large of an earthquake. So a terrible tragedy, and driven by poverty and the inability to build buildings to a high enough standard. So earthquakes are serious, and so there's a lot of research that's done to try to design earthquake resilient structures. For example, in San Diego, they have this large table where they can build a building. They build a small building on top of the table, and then they shake it back and forth. They can replicate existing earthquakes, or they can so they build the building. You can see the table there moving laterally, and then they take video, they take measurements, and they can study how different types of construction survive or don't survive in an earthquake. So this is an important part of research there. California obviously has a lot of earthquakes, and so it's something that's interesting there. Incidentally, growing up in California, even that Loma Prieta earthquake, I never felt. I could see the effect of it, but I couldn't feel it. The first time I ever felt an earthquake was sleeping in a hotel room in San Diego on a NASA trip just a couple years ago. Japan has a similar system for studying earthquakes. Theirs is even larger. And here you'll see this multi-story building subjected to an earthquake. And you can see that the first story columns actually fail. So this whole first floor has started to collapse, but otherwise the building stays mostly intact. So yeah, I'm not sure if you'd consider that a success or a failure. Probably you would survive and be able to get out of that building safely, but the building would definitely not be serviceable after the earthquake. So it's an important area of research. And how does damping come in? Well, there are a few different ways, but the thing that I thought was interesting to mention is that if you think of an earthquake shaking on the crust of the earth actually, as a ball, as a sphere, has its own modes of vibration. And so this the entire earth vibrates, and when you get an earthquake triggered somewhere on the surface of the earth, it excites all the modes of vibration of the earth. So this figure kind of shows you animations of a spherical, a breathing mode of the earth, and a football mode of the earth, or like an elongating mode of the earth. And so these are what the vibrations of the earth look like in some of its fundamental modes. This is the first mode with a 20-minute period. So a frequency of, 1 over 20 minutes, a tiny, tiny frequency. So it takes 20 minutes to go through one cycle of breathing. This one takes almost an hour to go through one cycle. Because the vibrations are so low, though, they last a really long time. This plot shows you the time in days after an earthquake or some event that excites the modes of vibration. And these are the frequencies. Notice the 10 to the minus 4 there. Really tiny frequencies. And so we'd have some of those fundamental modes here. You could read the slides later and see the different types of modes, but that football one, OS2, is an important one. And notice, though, vibration that's excited can still be measured many, many days later. And so an earthquake that happens in Japan, we can pick up measurements and triangulate it all over the earth. And we'll see the earth ringing for many days later. One interesting consequence of this, And there could be a lot more to this than just the duration of vibration. But when an earthquake happens, for example, in 2012, there was a very deadly, powerful earthquake off near kind of Japan, off Indonesia. And this earthquake, they mapped out all of the other earthquakes that happened a short time later, and you can see these patterns. So there's stress relief that in the plates that causes a static kind of relaxation of the stress everywhere else, and that can trigger earthquakes. But also remember that once this earthquake is triggered, the earth keeps vibrating for many days. And those vibrations, coupled with the stress and the strain in the plates, might be part of what triggers a lot of earthquakes. We definitely even saw that recently with the Utah earthquake, that there have been a variety of earthquakes in the West, and actually some in Europe even. So a higher concentration of earthquakes over the last few weeks, possibly due to this interconnectedness and as the earth continues to vibrate. So the earth has damping too, and we could take these curves and we could calculate what the damping is. The earth's a complex structure with a steel kind of liquid core, a rock crust, water, all these crazy things. But you put that all together and there's a certain amount of energy dissipation that happens as it moves. And in different modes of vibration, there'll be different amounts of energy dissipation. So some modes will decay more quickly than others. Okay, so an interesting example there. That concludes this lecture on damping. We'll see you next time.